By the way, are we having any difficulty with the edges? Anybody who's watching the videos? No?
No, sometimes I just have to put it to 1080p because it's a little...
I was looking at one of the videos yesterday, and the fisheye lens sometimes is more extreme than others.
Yeah.
Now, you guys all know you can enlarge the screen. You can always do the zoom in thing. But I just want to know if there's ever a chance that you're not seeing the edges. Because if there are, I need to know that, because then we need to change the position. I always like to make sure we get everything, you know. All right, so today we start the concept of series. Which is going to be our main theme for several weeks, and there's so many cool things we can do with this. There is so much mathematics that's going to take place that you didn't even know that math existed. The way I like to say it, we're going to answer questions where you didn't even know there was a question. Because the stuff we can do is so different, but so powerful. Now, I believe, Min, you gave me a great answer yesterday when I said, what is a series? You said, it's the sum of the terms of a sequence. So if we defined a general term of a sequence, an, now that means I've given you some formula. Maybe an is n squared. Maybe it's 3n plus 1, whatever. I've given you a general term, so now you can tell me a first, second, third, fourth, and on and on and on. Then we say, we call big S, S for sum, is the sum from n equal, usually it's n equal 1. It can actually start somewhere else. And what this simply means is A1 plus A2 plus forever and ever plus AN, and then we just forever and ever. It doesn't stop. It goes forever. So the first reaction most people have is, then wouldn't all of these be infinite? A lot of them are. How could I possibly have something not be infinite? What do you think?
If it's asymptotic or like is like converging to a point, to a value.
How would I converge? Well, if I just said, let's take a number, the number 5, and so 5 plus 5 plus 5 plus 5 plus 5 plus 5, pretty sure that's growing without bound. Yeah. But what if I said 5 plus 1 plus, a tenth plus 100th plus, right. What if my numbers are getting really small? That might work. And so we're going to look at all the rules that we need to do. So yes, it is quite possible I can have an infinite sum that adds up to a finite value. In fact, that's our whole goal in this course, is to, first of all, to find which ones do. If it doesn't add up to a finite value, that means the series diverges. Now, here's the part where before when we were talking about limits, a limit is finite, infinite, or a D&E. The integral, the improper integral, therefore converge to a number, it diverges to infinity, or the worst one, and we did one last day, it diverged without limit. Yuck. Yeah. But now when we're talking about a sum, we can only deal with sums that have finite limits on them, right? In other words, they add to a finite amount. So we're interested in the sums that converge. If it diverges, we're truly not that interested whether it's infinite or a D&E. It just simply doesn't converge. Since we can only use convergent series, a series is going to converge or it's going to diverge. The type of divergence, I mean, it's nice if you can say, oh, this one diverges to infinity, but this one diverges without limit. It diverges, right? It doesn't come to a finite value. And that's actually really where we draw the line in the sand. When I'm doing a specific limit of something, I'd like to know if that limit doesn't exist. That's true. Okay? So this is what it is. So right off the bat, and again, we use S because when you were doing baby algebra, you didn't do infinite sums, did you? You said add up the first 10 terms. In my discrete math class, we're doing finite sums. So what if I wanted to just do, let's say, the first 100 terms? What if I wanted to do this? Okay, so that would be A1 plus A2, A100. Is it possible this is infinite?
No.
Is it possible this is a D&E?
No.
No, it's just going to be some finite sum. Regardless of whether the original guy converge or diverge, this is going to be finite. So what we do is we label this one really cleverly S100. It's called the 100th partial sum. Now we're assuming we're starting at 1. That makes sense. That, I have a first term, second term, third term. But it turns out you can actually start anywhere you want. You're probably not starting at a negative number. But what if I said I'm not going to start till the 5th term or the 10th term or the 100th term? Where I start, this is a strange phenomenon, but where I start doesn't affect convergence or divergence. Let me write something here. Okay. Over the next few weeks, we're going to determine whether this particular series converges or diverges. We're going to learn a series of different types of tests. Now, I want you to stare at this for a moment. K is some finite integer. What do you think? True or false?
True.
Oh, good. We have a debate. Right? I always love when we have the argument. So what we do is we split right down the middle, right? And everybody stands there and does the whole thing, right? You guys have all seen West Side Story. Everybody's seen West Side Story, right? You have the two gangs, and they're getting ready to dance it out. You know, it's awesome. And they stand there and they do the whole rhythm thing. You know, it's the Sharks and the Jets, I think. I saw that when I was a little kid. It made such an impact on me. You know, that's the way all battles should be fought out, right? You dance it out. Kind of like Star-Lord does, right? Does he do that with Ronan? Doesn't he have a, I can't remember, like a dance contest, something. That's how we solve all battles. Is this true? Yes, it is. This says add up the first K terms, and now add up all the rest. This is always finite. If this diverges, it's because everything else diverged. Oh. Now, what if this part converges? Then I just add these two pieces up. Now here's why this is important. Let's say K is a big number. And I'm going to totally ignore this. I just lopped off a huge chunk of this series. But if this part's infinite, does it really matter that I lopped off a huge finite portion?
No.
No. So where you start. So if I said start here, rather than start at 1, start at 27. Will that affect the convergence or divergence? No. If it converges, it will change what it converges to because I just subtracted a finite number from another finite number. But if this diverges and I'm subtracting a finite number from infinity, it's still infinity. Does that make sense? That one is not always common sense. So it never matters what's happening early with a series. It only matters what's happening the rest of the way in terms of convergence versus divergence.
So could you just start at 99 and 100 just to see if it converges or diverges?
No, it's not it's this part that's going to determine convergence or divergence. Is that what you're asking?
Yeah.
Okay. So you make this?
Yeah.
It doesn't matter where we start. When we're doing our tests in a moment, it's actually doesn't matter where we start. It only matters what the AN is. So if I made AN, think of AN, make it a polynomial, something that's getting bigger. Then I'm adding numbers that are clearly getting bigger. That's going to diverge really, really quickly. It's getting, think of a parabola. And I'm adding all the y values. Wouldn't that grow ridiculously fast? Think of e to the x. Oh my gosh. But think of now e to the negative x. Now I'm adding numbers that are getting smaller, 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 smaller. Maybe that one converges. So I want you to get kind of a mental picture. So we're going to look at a couple of very specific type of series right off the bat. Most of the time, the vast majority of the time, if your series converges, you actually cannot tell me what it converges to, pencil and paper. You would need a computer to actually do something, okay? And I'm going to give you a really simple reason. For any series to converge, the terms have to get smaller. But they have to get smaller really fast. So they have to get way smaller, way smaller, way smaller, way smaller. So what's happening is as I'm adding them up, I'm only changing further decimals. Do you remember when you first derived E? Remember the whole loan sharking example, right? We increased the number of times per year we compound it, right? You guys remember doing that? And what did you notice? The changes occurred further and further out. Eventually, only the pennies were changed. And then eventually, even it's past the pennies that were changed. That's what happens if something converges. The changes are further and further out, so we can see exactly what it's going to converge to, but that would require technology. We're not worried about that. Our goal is to determine convergence versus divergence, and then I can always use technology to give me a reasonable number. Okay? That's a completely unrelated animal. So, let's start with the first one. This is what is called a telescoping series. Okay? Now, let me start with something really simple. So n equals 1 to infinity. And we'll do, how about 1 over n minus 1 over n plus 1. Let's start with something that's simple. So just to kind of get a feel, maybe write out the first couple of terms. That's always a good idea. So what would the first term of this be in parentheses?
1 minus 1 over 2.
And then the second term would be what?
1 minus 1 over 3.
Uh,
Or 1/2.
So now 1/2 minus 1/3. We'll do another one just to make sure. Then 1/3 minus 1/4. So overall, I'd have a half plus a sixth plus a 12th, and this is going to go on forever and ever and ever. Well, I don't know. This is going to be kind of tricky to see a pattern. So here's the trick, and we're going to use this trick a couple of times. What we're going to do is we're going to find Sn, which is the sum of the first n terms. That has to be finite. And then we're going to calculate S by taking the limit as n goes to infinity of Sn. This is a really clever way, if it's possible to calculate a sum, find a partial sum, which means there's going to be an n in my statement, isn't it? Because I didn't give you a specific value for n, so there's going to be an n in there. And then we'll take this limit. Okay? So this works beautifully here. So let me undo this. I want to just do the first n terms. So I'm going to write Sn. So Sn is going to be 1 minus a half plus a half minus a third. I'll do just a few. Plus a third minus a fourth. Now, I'm going to keep going. What's the very last term? Well, won't it be 1 over n minus 1 over n plus 1? Won't that be the nth term?
Right.
What will the term right before it be, by the way?
1 over n minus 1.
It'll be 1 over...
n minus 1.
Careful. Let's see. Now that's probably not, it's probably not going to be as helpful if I write it that way. But yeah, it'll be 1 over n minus 1
minus 1 over n.
minus 1 over n. And then that term will be 1 over n. I think it might be more useful to write it like this. Now, let's assume n is really, really large. Do you really want to do, okay, calculate that, then calculate that, then calculate that, then calculate, you really want to do that?
No.
Does anybody see anything jumping off the page here? You know, let me stand back here. Let's see, I have 1 minus a half, but then the next one starts with a half minus a third. What do you think? I am adding. Can I just simply remove the parentheses and go like that?
Yes.
Oh, okay, that felt good. Can I do it again?
Yep. Yeah.
Can I do it again? Can I do it again? Does every single term cross off?
No,
Almost. What didn't cross off?
the first and last term.
One,
Well,
the first
one
and last.
and
We like this problem. In case you didn't know that, you like this problem. Why? Because it's really simple. It's one of the few times we actually can come up with a specific value without doing anything clever. You might call that clever. No, this is just an observation. So, what is Sn? What is the sum of the first n terms? Not the infinite sum. I just added up the first n terms and I stopped. So what is that sum exactly? Does everyone agree? That's exactly what it is. That's the sum of the first n terms no matter what n is. So if you wanted to just sort of trial and error to make sure you got it right, just do 2 or 3 terms, see if you got the same n. What did we start with? When we did the first 3, we got a half plus a sixth plus a 12th. What's that? That's 6/12 plus 2/12 plus 1/12, that's 9/12. That's 3/4. If I replace n with 3, wouldn't that be 1 minus a fourth, which is 3/4? In other words, I got the same number. I'm going to be lazy. I'm not going to go past that. That's the sum of the first n terms. So what's this going to be? Like this. Well, isn't this a transient term? Doesn't that term go to 0? So what's my limit? 1. That's kind of cool, isn't it? This thing here adds up to 1. So what if I said, I'm going to use a computer. How many here have ever written any computer code at any level? Okay, Probably the simplest thing anybody did was a do loop. I mean, I taught programming the whole decade of the 90s, and that's literally day one. For I equal 1 to whatever, do. And you just have it do this. So just for fun, we're going to write a program. Anybody who's done programming knows this is actually really, you probably have less than 10 lines of code. And let's say you want to add up the first 1,000 terms. You're not going to do it by hand. You're going to let the computer do it. You're going to add up the first 1,000 terms. Well, you already know what the answer is going to be. It's going to be 1 minus 1 over 1,001. But no matter how many terms I add up, will I ever see the sum equal 1? No. It's just going to get closer and closer and closer, and 1 is a limiting factor. 1 is the limit. I'm never going to see a 1, but 1 is the limit because I said you're going to do this forever. Do you understand? I can't do that on a computer forever. I can't take that limit. Okay? So a telescoping series is basically one where terms cancel. I wrote one where the first and last one were the only ones left. It could be maybe the first two and the last two. There's a lot of ways that anything it can be done, but that's a telescoping. That's interesting. That's not the most important one. Okay. There's one that's far more important that we're going to look at today. So last day when we talked about sequences, we talked about a geometric sequence. This one is very important. So if you remember, the definition of the geometric sequence was one where consecutive terms had the same ratio, which is the same as saying, I'm going to get my next term by multiplying this term by that ratio. So I'm not adding the same amount, that's the arithmetic. This one I'm multiplying by the same amount, if you will. So we did an example last day. Let's say like 2, 6, 18, 54, 162, blah, 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 blah. Right? That divided by that's 3, 3, 3, 3. Okay. This is geometric, which I can see an exponent forming. And then we figured out a general pattern for this, right? But if I wanted to add up these numbers, they're getting really big really fast, aren't they? That would make me think that this thing is going to go off to infinity, and it will. It will. But what I'd like to know is there a simple way to add up all the numbers? And this is something you probably did in an algebra class way back when. So let's look at the geometric series. So we know we have A1, and then the second term is A1 times R, and then the third term is A1 times R squared. Remember, we did this last day. What is the nth term?
A to the R n minus 1.
Good, because there's no R on the first term yet. I want you to add up these terms and give me an actual total, because remember, we want to take a limit. So, piece of cake. I want you to add up this. How do I add these up? Yeah, I can factor out the A1, but how do I add R to R squared to R cubed? That's not obvious. Okay, do we all agree that this is Sn? That's the sum of the first n terms. Just for fun, because you know it's always our ultimate goal, I would like you to take negative R and multiply it by Sn. Just for fun, because that's really not that hard to do. So if I said take negative R and multiply it by Sn, what would that be? That'd be negative A1R. Agreed?
Right.
And then what? The term right before this, by the way, would be negative A1 R to the n minus 1, and then L. Okay. Everybody agree with that?
Yeah.
Okay.
Do you see anything clever we could do here?
No.
What do you think?
Isn't it still growing without bound? But
Well,
just
but no,
negatively?
that's entirely dependent on what the value of R is.
Okay.
We're not worried about convergence or divergence yet.
Okay.
We just want a partial sum. I would like to be able to add these up. Imagine n is really large, so it's completely impractical to add up 100 or 1,000 or 1,000,000 terms. I don't want to do that. At the telescoping series, what did we do? We figured out a way to add everything up, and we ended up only adding up 2 numbers, right? So think of the telescoping series. I want n literally to be a bazillion. And it still took us the same amount of time. Just we only considered the first and last. Does anybody, what if I add up these two?
So it always cancels out except A1 and negative.
Do you notice? Oh my goosh. It has the same kind of feel, doesn't it? It's not a telescoping series. We just did this clever move. If I do this, what am I left with?
And, yeah.
I'm left with this one, and I'm left with this one, correct? So what does that give me? I'll bring it up over here so you can see it. So now I have Sn minus R times Sn, and that's equal to A1 minus A1 times R to the n. By the way, this is true no matter what the value of A1 and R are, because we started with the geometric sequence, and I just said let's add up the first n terms, and that's what we're going to get, period. But I still don't know what Sn is, but can I do a little factoring here?
Yeah.
So if I factor the Sn out of the first term, that'd be a 1 minus R. How about at the same time if I factor the A1 out of this term? Can I now say this?
Yes.
And this is the formula for the nth partial sum of a geometric series. Now let's go to the next step. When will the series converge versus when will it diverge? Well, common sense. If R was a large number, 1 minus R is just a constant, A1's a constant, but that R to the n is getting really, really big, isn't it? Let's keep it simple. Let's just say R was 2. And I said 1 plus 2 plus 4 plus 8 plus 16 plus 32. My numbers are growing without bound, aren't they? That's a piece of cake. Here's one you guys have all seen. All right, every 5 seconds I'm going to walk halfway across the room. Halfway of whatever's left. And then half of that. And then I'm going to walk half of that. And then I'm going to walk half of that. How long will it take me to get to the other side?
You'll never reach it.
Well, no, how long will it take?
What is it?
How much time will it take for me to get to the other side? Would you say there is no time? No, be infinite, wouldn't it? Funny thing about calculus, we actually have infinite time. So if I wanted you to add up halfway across the room, and then half of that was a fourth, and then half of that was an eighth, and half of that was a 16th, and so on and so on and so on, what do you think those would add up to if I added them up forever?
You'd never get
What?
there.
No, if you added them up forever, we can take limits, guys. That's trivial. The easiest part of every problem is going to be your limit to infinity. Yeah, max S is going to add up to 1. Yeah, but the limit, is there ever a point when these added up to 1? No, but the amount left is getting smaller and smaller and smaller and approaching what?
1.
The amount left
Approaching 0.
is approaching 0, which is why the infinite sum. Now, most of you have seen that probably in a high school class, right? I always laugh because in high school class they'll call those infinite series, which is kind of redundant because the word series already means that it's infinite. There's no such thing as a finite series. It's like saying a finite infinity. No, an infinite series, that's kind of like the straight line. You all say that, right? A straight line versus all those other crooked, bent, curvy lines. I always, that's from what they call the Department of Redundancy department, something like that. Yeah, a series is infinite, period. We added up the first n terms. Now here's our goal. I want to take a limit of that. I'd like to know, does this series converge or diverge? Well, I think we all agree it kind of depends on R, doesn't it? Because if R is big, clearly this is ballooning up, but maybe there are values of R that don't. So I want to just focus on R to the n. So you need, get out your calculators, please. Oops. I don't care about the A1, that's a constant. I don't care about even just the R itself, that's a constant. I'd like to know what's R to the n doing. Well, get out your calculator for a moment and then we'll just have some fun. Put in a number bigger than 1 into your calculator. I don't care how big the number is. Just put in a number bigger than 1. Put in 2, put in 10, put in 100. Now raise it to an absolutely absurdly large power. You're going to get a finite value. But what does that finite value look like? Is it astronomically large or is it really small?
Math error.
It's too big. I think we all agree that this limit would be infinity if R is greater than 1. Why? Because really simple. What is the shape of an exponential function? Exponential functions only have two shapes. And we did this way back at the beginning of the course. An exponential function has two shapes.
Either diverges to infinity.
That's called exponential growth. And that's called exponential
Decay.
decay. What's the difference? This is y equals a to the x. This is y equals, we'll call it b to the x. A is greater than 1. B is between 0 and 1. Can't be negative, by the way. Oh, okay, so if I have an exponential function and the base is between 0 and 1, that means my numbers are getting smaller. My base is bigger. We know this. This isn't calculus. We know this. So this is really easy. Now, take your calculator. Now, let's, just for fun, put an R of 0.999. That's like saying I'm going to lose 0.1% every year of whatever I've got. I got a little bit of degradation there. Do 0.999 and now raise it to an absurdly large power again.
0.
Whoa, does it equal 0? I just took a non-zero number and raised it to a power. Can that equal 0?
No.
No, but what's your calculator saying?
0 because it's approaching.
It was too small for it to now register. It had more than 99 zeros after the decimal place. That's what it actually means. Whoa, it couldn't even give you a scientific notation answer. It was so small.
Yeah.
Now you gotta admit, that's kind of cool. I took a number really close to 1, I raised it to a very large power, and what happened? Well, it's still decay, isn't it? So here's an easy one. It's going to be 0 when? If R is less than 1, ooh, careful, wait a minute. What if I take, negative 10 and raise that to a large power?
Between negative 1 and 1?
So it would go back and forth between positive and negative.
Change it. Oh. Because if I take a negative number and raise it to a power, you're right, it's going to oscillate in sign. But a negative big number, won't that still get huge? So the negative big number is the most evil. Negative big is evil. Because what if R is less than negative 1?
If
Let's
n
just
is,
say R is negative 2.
if n is even, then it'll be infinity. If n is odd, then it'll be negative infinity.
But n is approaching infinity. N isn't ever stopping. Oh gosh. This, by the way, this is my favorite type of divergence because it's the most evil one. Remember, you guys know that. Sometimes evil is fun, right? I mean, my oldest son, he used to love, he rooted for Darth Maul every time there was a fight. He cheered for the dinosaurs in Jurassic Park when they ate the people. He's like 3. He always rooted for the bad guy. Because the bad guys, let's face it, Luke Skywalker is boring, right? Darth anybody is more interesting. So, I have something, it's small and I'm raising it to a power. It's like negative 2. I'm running out of room really quickly. What's happening? It's oscillating but getting bigger. This is the absolute worst type of divergence. This is diverging without a limit, but like Chase said, depending on whether n is odd or even, it's ballooning but in both directions.
It's oscillating between infinities.
This is definitely a DNE. But it's the worst kind of DNE because it's approaching positive infinity and then the next one's approaching negative infinity, then positive infinity. So it's not even approaching a sign, is it? So this is DNE. Well, then that leaves us 2 values left. What are the 2 values left?
Equals 1.
Negative 1, same thing. Negative 1 to a power is just going to oscillate between 1 and negative 1 forever and ever and ever. So I'll put the or equal in here. Then there's one more. R, what's the only one we haven't used so far?
R is equal to 1.
Oops. I want you to take, I have a geometric series where R is 1. That's probably the most boring geometric series. And my first term is a 4. Then what's my second term? A 4. And then what's my third term? Anybody want to go for the 10th term?
It's gonna
100th term? Aren't I adding the same number up now infinitely many times? What's that going to be? Infinite. That's boring. So we have only one situation that we can consider. It's that one. That may not have occurred right away. Now, in a baby algebra class, you may have gone over this. You may have seen this at one point in your life, but probably wasn't recently. So, I've got R to the n. R to the n is going to diverge in almost every situation except this one. This is the only situation where it's going to converge. And that's the one we're going to focus on, because that's the only one we truly care about. Remember I said if it diverges, we're not interested because we can't answer any questions. So going back to this statement here, as long as the absolute value of r is less than 1, and we say absolute value, you said it before, it's got to be between -1 and 1, but it can't be inclusive because the 1 and -1 would cause me to diverge. So if I take any decimal that's between -1 and 1, -0.5, +0.8, doesn't matter as I raise it to larger powers, but the negative's going to oscillate, but it's going to go like this. Right? It's going to zero in on something because it's getting smaller in size. Okay? So now, the infinite sum. It's the limit as n goes to infinity of that. You know, like this one, because this one has so many uses. Yeah.
I have a question about the limit. When r equal to 1, this one raised to any power this 1.
I'm sorry, say again?
Like the limit of r when r is equal to 1, is it raised to any power
Well,
this 1?
okay, this formula won't hold exactly if r equals 1. So this formula is for everything except 1, but think of it logically for a moment. Oh, I'm sorry, you know what? You're right. Sorry, you're right. This is 1. The sum is going to be infinite. Sorry, the sum is going to be infinite, not the r. Yeah, good catch. Good catch, Mitch. That's going to be a 1, but the sum is going to be infinite because what am I doing? I'm going 1 plus 1 plus, or r, a1 plus a1 plus a1 forever and ever and ever. So I'm glad you caught that. Okay. I want to do this, so if the absolute value of r is less than 1, then we can evaluate this. If the absolute value of r isn't less than 1, it's going to diverge, period. And right now, we're not that concerned whether it's infinite or d and e, it just diverges. But if the absolute value of r is less than 1, then what is happening to this term right here?
0.
That term's approaching 0. Which means my answer is, oh, that's it. That's my answer. My answer is simply the first term divided by 1 minus r. I would like you to add up. I'm going to take a half plus a fourth plus an eighth plus forever and ever and ever. My halfway cross, halfway, halfway. I want you to add those up. So it's going to take you a while, right? Because there's an infinite number of values. Is this a geometric series?
Yeah.
Yes. All I need to do is identify the first term and the r. What's my first term? Okay, that's easy. A half. What's my constant r?
1/2.
It's also a half. Okay, that's coincidental. I don't need to take a limit. I just need to do that. So what do I get? A1 over 1 minus r.
1.
Kind of cool, huh? If you have a geometric series and your ratio is smaller than 1 in absolute value, then that series converges, and it converges to exactly that. You don't have to do any work at all. You just have to identify. The telescoping and the geometric are basically the only ones that we can absolutely say, here's what it adds up to. Everything else is get a little more dicey. But these are extremely useful. In fact, the geometric is one of the most important, because as we go down the road and we do all of our different tests, a lot of times we're going to compare things to a geometric. And you used the term asymptotic. We're going to look at things that are asymptotic to geometric, and if the geometric converges, then the other one probably converges because it has the same behavior, even if I can't tell you a number. Now, this is actually one of the most practical things. Some of you remember, maybe you did this in algebra, maybe you did this in pre-calc. Okay, what is the definition of a rational number? Do you remember? The definition of a rational number in words. It's any number that can be written as a
Fraction.
quotient, well, yeah, quotient of,
2, not 2.
Rational, real number.
all three of these are quotients. Only one of them is rational. The definition is very strict.
Integers?
The first one is a fraction because it is a quotient of integers. A quotient isn't a fraction. A quotient just means I have numerator and denominator, but if I have a quotient of integers, that's a fraction. That's a rational number. That's irrational, that's variables. So if a rational number is any number that can be written, can be. That's why all integers are rational, because the number 5 can be written how? 5 over 1, 10 over 2, 15 over 3. Aren't there an infinite number of representations of one number, if I think of it as quotients? Yeah. That's why all integers are rational, because they can be written as a quotient of integers. But an irrational number isn't, because it can't be written as a quotient of integers. Now, that's the simple definition, but there's also a decimal version. And this one is the one we're going to use now. Because this is how we distinguish rational from irrational. Simply to tell you, well, an irrational number can't be written as a quotient of integers. That doesn't tell me what it is, though. It tells me what it isn't. See my point? How do I know root 2 can't be written as a quotient of integers? Because all numbers either have terminating decimal places, all numbers. Somebody, give me some decimals for root 2, please. Just on your calculator. I can do the first couple. 1, 4, 1. Give me several.
4, 2, 1, 3, 5.
Okay. I'm going dot, dot, dot. Goes forever, never, never. We know that. All rational numbers either have a terminating decimal or they have an infinite decimal. Well, those are my only two choices. But the infinite decimal has what? Do you remember? A repeating pattern. It doesn't mean one number is repeating. It means it could be 10 numbers, but it has a repeating pattern. All rational numbers, if I convert them to a decimal, like 1/2, that's terminating, but 1/3, that's infinite with the repeating pattern. Therefore, what's the definition of an irrational number? Infinite decimals, no pattern. In other words, I'm going to tell you the first decimal is 3. Can anybody here tell me the next one? I think you can. It's 3. But what about the 7th one?
3.
Okay. Can you tell me the next decimal? Nope. There's no pattern. Pi, you'd have to memorize, but there's no pattern. There's no repeating pattern. So if I use this version of a rational number, everybody here, if given a fraction, you put it on your calculator, you can tell me a decimal. And as long as the repeating pattern isn't more than 10 terms, you can put the bar over it. So what about in reverse? I'll do something simple. I have 0.36 with a bar. I'd like to know what the fraction is. Now, of course, all of you have memorized every fraction's decimal equivalent, right? You've all got that. You did that probably, I don't know, last year, maybe the year before. So every single fraction that exists, you guys already know the decimal equivalent, right? Yeah, everybody knows that. And you know the infinite repeating patterns of all things. Or maybe not. Can you tell me what fraction this came from? Well, I could memorize. Well, that would be inefficient because I'll just throw more decimals. Is it true that this is 0.36363636? Okay. The dot, dot, dot means continue. Is that true? Is that true? You know, if I didn't know any better, I'd say consecutive terms have the same ratio, which means this is a geometric series. In fact, every repeating decimal pattern is a geometric series automatically, no matter what, which means that if you are ever given the repeating pattern of decimals, you can always tell me what fraction it came from. Some of you may have done this. I would hope that you did this in an algebra class way back when. I don't care if you remember how to do it, because it is such a cool thing that we can do here. All right, so what is my A1?
136.
0.36. What is my R?
1/100.
Yeah, I'm going to write it as a decimal only because the other one's already a decimal. So, do you all agree with that? Yes, it's 1/100 because I'm moving 2 spaces at a time. Everybody cool with that? Can you now tell me what this equals? Yeah, first term over 1 minus R. Well, that'd be 0.36 over 0.99. Can I keep going? Well, how about 36 over 99, which would be, how about 4 over 11? Huh? On your calculator, put 4 over 11. What do you see?
13636.
Oh my gosh. Do you see 363636? How many have done this before? what I just did. How many have done this in the class before?
Nope.
Oh, do you know this was this is algebra 2. But last or second to last day of the semester in every algebra, this is every Math 96 on planet Earth. This is part of the curriculum, and it's also part of the curriculum in every pre-calculus course. So if you haven't seen it, I mean, somebody shortchanged you. Maybe you should go back and get your money back or something. Yeah, this is actually stuff you would have seen in a lower level course. Do you need it? No. But now you say, oh my gosh, if it's geometric in nature and the size of the R is small, it's going to converge, and I can actually tell you exactly what it converges to. That's kind of cool. It's kind of cool. One of the reasons in math we like to leave things as fractions, because anybody can convert a fraction to a decimal. Anybody can convert an irrational number to a decimal. But if it's irrational, you can't go from the decimal back to where it came from because it's already been rounded. But when I write the bar over the top of something, I can always go back. I just showed you right here. So the geometric is very powerful. Telescoping is more just interesting. Geometric, way more important. Those are the two that we can actually find the sum when it exists. Now let's keep going. Okay? One of the most important series that we're going to use all the way through is something called the harmonic series. Now, what's kind of confusing, I'm a math person, and one of my pet peeves is when we use a specific word and give it multiple meanings depending on the context. I don't like that. I really don't like that. In my differential equations class, they just had their first test last week, and they were mostly solving homogeneous differential equations. That means simply the equation equals, does anybody know it? All homogeneous equations mean they equal 0. That's what it means to be homogeneous. But then one of the problems, they had to solve a problem that had something called a homogeneous function. That has absolutely nothing in any capacity to do with an equation or the number 0. It has a very specific definition. A homogeneous equation and a homogeneous function, the use of those two words have nothing to do with each other. As different as you can possibly be. So why did we use the same word twice? And they did a homogeneous function within a homogeneous equation. That's not confusing, is it? That's terrible use of the term. There are several terms mathematically that we use. Harmonic is another one. Harmonic motion, we mentioned that last day, didn't we? Harmonic motion generally refers to what? What's the word? An oscillation. Yeah, that's why sine waves, cosine waves. Harmonic motion is an oscillation. I talked about damped harmonic motion means the oscillation is getting smaller, right? I used shock absorbers as an example. That's harmonic motion. That's what you're going to study in physics and different things. Harmonic series has absolutely nothing to do with that. The use of the word harmonic is not even related to that one. And again, this is considered maybe one of the most, if not the most, one of the most important series. Why didn't we give it a different name? Right? Because we do get confused. We're not going to do harmonic motion in this context, but we actually can. We can talk about hitting something and then adding up all the bumps. This is the harmonic series. If I put a negative, let's see, if I raise this to, a power or something and have it oscillate, I can make it harmonic motion. I don't want to do that. So what is this one? This would be 1 plus a half plus a third plus a fourth forever and ever and ever. If you know how to use the summation key on your calculator, does anybody here know how to use their summation key? If you have a graphing calculator, you have a summation key. So what I used to do, there was a time many years ago that every single person in every single math class had a graphing calculator. Everybody had a graphing calculator. Now, how many here have a graphing calculator physically with them? A handful, that's good. I really like graphing calculators because they're really, really good for graphing. But they're also really good for this kind of thing, because you can't do this on a cheap calculator. So what I would have people do is I'd say, okay, well, somebody go ahead and add up the first 1,000 or first million. Just do that on your calculator and tell me when your calculator is done totaling. So if I gave you 1,000,000, maybe in an hour you're waving at me going, I have a number. I believe the sum of the first 1,000,000 is somewhere in the neighborhood of about 14. It's not very big. Some of the first billion is, I don't know, I don't even think it hits 20 yet. So obviously these aren't getting very big. Actually, I'm going to prove to you that this is infinite. This is why this one's so important. It doesn't seem like it should be, because if I actually use technology to do partial sums, the first 1,000,000, the first billion, the first trillion terms, I'm always going to get back small numbers. But unlike the E, where as I kept going, the number kept getting bigger, but the changes, remember, occurred further and further and further out. The changes here will still be taking place in the first digit constantly. So the first digit will always be growing, and eventually you can get into the hundreds, eventually the thousands. It takes a long time. It's the slowest moving series. So how would I prove that this divergence? You're going to like this. It's so simple, this proof. And it's, by the way, there's a much better proof that we're going to learn next day, but we don't have that tool yet in our tool belt. All right? So what I'd like to do is, this goes forever. I would like to group it as follows. 1 plus a half plus a third, plus a fourth plus a fifth plus a sixth plus a seventh, plus an eighth plus, I'm not going to write them all out, plus a 15th, plus a 16th plus a 31st. Okay, can everyone see the pattern that I'm creating? What's the first term in each of my groupings? It's going to be 1 over 2 to a power, isn't it?
Right.
So I'm going to do this, and the next one's going to be 1 over 64, the next one's going to be 1 over 128. How many groupings am I going to have? Infinitely many. Now here's the important thing. I have 2 terms. One of them's a half, one of them is bigger than a half. Is it safe to say that that sum is bigger than 1? What do you think? Yes or no?
Yeah.
I have 4 terms. One of them's a fourth. I'm sorry, you know what? I think I just did this. Oh, you know what? My bad. I just realized something. I got my parentheses shifted by 1. I'm sorry. I just realized I shifted my parentheses by 1. My bad. Sorry. I wanted to go that way. And then the next one is, I said starts with, ends with, not starts with, sorry. So this would be 16. And that's not going to work otherwise, is it? So that's now 17, and that's going to be 32, and that's going to be 33, and that's going to be, there we go. Okay. I'm going to end, my bad. I'm going to end with the 1 over 2 to a power, not start with.
Oh.
Sorry. So I just shifted my parentheses by 1. Now, I have 2 numbers. That's a fourth. That's bigger than a fourth, so that's bigger than 1. I have 4 numbers. Bigger than a half, sorry. I have 4 numbers. That's an eighth. These are all bigger than an eighth. That means this is bigger than 4/8. I have 16 numbers. That's 1 over 32. These are all bigger than 1 over 32. So this is bigger than 16 over 32. As I do this forever and ever, tell me about each grouping. It's always going to be bigger than a half. How many groupings are there? Infinitely many. I'm adding up infinitely many values that are all bigger than a half. What will that add up to? Infinity. I'm adding up a number bigger than a half infinitely many times. That's kind of a crude brute force proof, but it's beautiful, isn't it? By simply being clever in grouping. Now, you can't always do this, but this had such a nice pattern. The harmonic series is one of the slowest moving divergent series there is. But it is very important because it's kind of a line in the sand series. When things are on one side, I can say they diverge. When they're on the other side, they might converge. And we use that tool tremendously over the next few days. So this one is very powerful. Now, let me show you a couple of simple rules of sums. In Calc 1, I go over these because before we integrate, we always do things. But remember, we did the Riemann sums, we did the rectangles, we added them all up. And in some cases, we were able to use some of the summation formulas. But we did summations. So let me do, first of all, finite sums. I'll use I1 again. There's only 2 rules that I'm going to review. And it's how to add some. So those in discrete math, you saw this yesterday. It's the same rule. This says A1 plus A2 plus A3 plus A4 up to AN. This says the same thing. I'm starting and ending at the same number. That's important because I have the same number of terms. Okay? Well, let's see. That means this would be A1 plus A2 plus A3 all the way up to AN plus B1 plus B2 all the way up to BN But if the A's and B's are simply real numbers, they're not variables in this case, they're actually real numbers. Can't I use commutativity? Mike, would you mind going and closing it? Usually they wait till I have an exam to do all the crashing and bashing. Every exam I ever give, there's a crashing and bashing effect. Can I rearrange and regroup these? They are just numbers. Now, why would I do such a thing? This is the first major result. The summation, the sum of the summations is the summation of the sum. I can add or pull apart. So if I started with something like this, I can also pull it apart in order to answer the question. You're going to find that be useful, going in both directions. The limit of a sum is the sum of the limits. Derivative of a sum is the sum of the derivatives. Integral of a sum is the sum of the integrals. There's a few other places in math where that holds true. Well, is there another property that limits derivatives, integrals, and things share? Not just sums, there's one more. Think about it. Limits, I can do everything. Limit of a quotient, quotient of the limits, limit of a composition, composition of limits, but that's not true with derivatives and integrals, is it? But there's one other one, sums and scalar multiples. What if I do that? Well, that would be k times a1 plus a2 up to an, which would, if I distribute, be ka1, ka2 up to kan, but that's the sum of...
Right.
Oh. So that's a limit property, that's a derivative property, that's an integral property, it's a summation property. The scalar times the summation is the summation of the scalar times the original thing. What does that mean? That means you can pull things in and out, constants, not variables. And so sort of the final version most people use, and there's a term you haven't learned yet, you're going to learn and use on a regular basis. But I'm going to write it like this. C1 is just some arbitrary constant. C2 is just some other arbitrary constant, not the same one. So if I put those together, sums and scalar multiples, does anybody know what that term is called when you take constant multiples of things and add them together? It's called a linear combination. That's going to be a very important term you're going to use in a lot of classes after this one. So the linear combination of the summations is the summation of the linear combination. So that includes sums and scalar multiples. This allows us to manipulate certain things. So I would like you to determine the convergence or divergence of the following series. Does this converge or diverge? I don't want a proof.
Converge.
Oh, good. Okay, guys, you ready for the standoff? Come on.
It converges because if n keeps growing.
Is
Without
this
bound.
statement true? Is this true?
Mm-hmm.
And what did we just prove? That that's infinite.
What?
That was all that about.
Oh.
That's the harmonic series.
Mm.
Oh, I just took something that's infinite and I multiplied it by 10. Is it still infinite? Yes or no? Yes. So did I have to do anything? No, I just had to recognize that a previous result was smack dab in the middle of my problem. I erased it. Okay, it was over here. This is the harmonic series. This is now 10 times the harmonic series. So this diverges, and I'm going to put in parentheses, to infinity. That's nice, but it's really, it diverges. That's the more important thing. Because what if? Let me change one thing about this problem. I just put a negative in front of that. So, is that true? Does it still diverge?
Yes.
Yes. Does it diverge to infinity?
No, it diverges to negative.
To negative infinity. That's still divergent. The fact that it diverges, the negative versus positive is less concerning. It diverges. And in fact, it's infinite in nature. It's just negative. There are textbooks that will actually tell you you can't do series with negative terms, which is an absolutely incorrect statement. My God. What you're going to find is, at the end of the line of all this, almost all series are going to alternate. Almost all the series we work with are going to alternate signs. And so when the textbooks say, well, you can't do anything with negative numbers, you're never going to do anything that doesn't have negative numbers in the problem. So yeah, negative isn't a problem. It just means my final result might be a different sign. That's not a big deal. I mean, that's kind of an easy thing. Okay, before we move on, any questions? So we've looked at 3 very specifics. The telescoping series, I can tell you what it adds up to. The geometric, I can tell you what it adds up to if it converges. How will I recognize if it doesn't converge? Because not everything's going to converge. In fact, probably most things won't. All right. Just for fun. N equals 7 to infinity of negative 4/3 to the nth power. God, that just looks scary.
Well,
Not really.
that,
Does not exist.
that's 4/3.
Does this converge or diverge?
Negative
Divergence.
4/3.
Well, this is kind of tricky because it's not that one. What's my very first term?
Negative 4/3 to the 7th power.
What's my next term?
Today.
Negative 4/3 to the, yeah.
Oh, so what's my R? Negative 4/3. What's my A1? Whatever that is, I'm not going to calculate. Does it matter what my A1 is?
No.
No.
What is your conclusion and why?
It
R
diverges.
is smaller than -1, so it diverges.
It diverges, how about if I write it this way, since the absolute value of negative 4/3 exceeds 1. That's all I'm going to say.
Right.
If you said less than -1, that's okay too. I don't want to have to worry about directions. Does everybody understand what I just said? My R in absolute value was too big. So this is the worst kind. This is the oscillating getting bigger in each direction. Yikes. The fact that I started at 7, did that have anything to do with my conclusion?
No.
What if this converged? Yeah, then starting at 7 matters because I have a different first term. So it would mean I'd get a different numerical total than if I'd started at 5 or 3 or 1. But because it's diverging and I lopped off the first 6 terms, the first 6 terms were finite. But this diverges because the R was basically too big in absolute value. So there wasn't much work to perform. This was identification. If I change this to, let's say, negative, let me go like this. What if I make that negative 2/3? Is this going to converge or diverge?
Converge.
It's now going to converge because it's small enough now. Now all I have to do is my bottom is going to be 1 minus R, and my numerator is going to be whatever the first term is. And then I just use my calculator. Piece of cake. That should be fairly simple. You don't need to take a limit because we derived a formula. I don't need to take a limit. I need to take a limit on the telescoping because I have an N. But I don't need to take a limit on the geometric. I already know what the answer is going to be. Okay? Now, the next thing we're going to do, this is a really important one, but it's a different kind of philosophy that we're using. How many have ever heard the expression necessary and sufficient? It's a mathematical thing. Necessary and sufficient conditions. A lot of people get them confused. If you understand conditional and converse and inverse and contrapositive, they kind of fit in. A necessary condition is sort of the least amount that must be true for you to carry on. A sufficient condition is enough for you to get a conclusion. So, a necessary condition for us to win the game today is that we actually show up. You know this. Because if we don't show up, we lose. A necessary condition for us to win is that we actually show up. Does that mean we're going to win if we show up? No, it means now we might win, there's going to be a game played. Whatever a necessary condition is does not guarantee a conclusion. If you have a necessary condition, its failure guarantees you won't have the conclusion. See what I mean? So if the minimum for me to win the game today is that we actually show up, then if we don't show up, we absolutely lose. A sufficient condition for us to win is that we outscore our opponents. So we outscore our opponents, are we going to win? Yes. We like sufficient, that's more powerful, but we're working with what's called a necessary condition. So there are two, and most people just refer to this as generically the nth term test. A necessary condition for convergence is that I pass these two things. Passing these two things does not mean I will converge. No. Failing either one of them guarantees that I diverge. So some textbooks refer to this as, by the way, this is a terrible title. They refer to this as the test for convergence. No, this is not the test for convergence. Everything else we do is the test for convergence. This is not the test. Yeah, no, this is a necessary condition for convergence. So the first one is, we're starting with something of this form, by the way. First one is that the limit as n goes to infinity of an is actually 0. Now, let me give you a really simple example. All right? So I'm thinking of a sequence that looks like this. So my first term's going to be a 1. My next term's going to be 1 1/2. The next one's going to be 1 2/3, and 1 3/4, and 1 5/6, and so on and so on and so on. If I asked you for the limit as n goes to infinity of an, what's the answer? Pretty obvious. 2. So my sequence converges to 2.
Right.
Now, I am interested in the sum. I am now going to add up an infinite number of numbers that are all approaching 2. Tell me about that sum. I'm adding up an infinite number of numbers that are all approaching 2.
Infinity.
That's kind of like saying I'm going to add up 2 infinitely many times. That's clearly going to be infinite, isn't it? Oh, my sequence converged to a finite number. But my series is clearly going to diverge because I'm adding up positive numbers that are getting closer and closer to 2. So it's like saying 2 plus 2 plus 2 plus 2 forever. So this is going to diverge. In fact, this is going to diverge to infinity because these numbers is getting infinitely large. Why? Because this didn't go to 0. I failed that condition. The second condition is that I'm putting it in absolute value because we can have negative terms. That's not a problem. We can even have alternating signs. That's not the problem. I want the size of the numbers. Remember, we talked about a geometric series. If r is negative but small, it's going to go like that. And each term is smaller than the one before in absolute value. But you're going up, you're going positive, negative, positive, negative. Or what if all of my terms are negative? Oh. So if this happens, if every term that comes after is less than or equal to the one that came before, for all, that's called the universal qualifier, for all n bigger than, we usually just put some number. Simple English. It might be the first term, it might be the 10th term, it might be the 100th term, but eventually my terms are all going to get smaller from that point on. They can, and by the way, we're going to look at things like this that will confuse us. We're going to look at things that the terms balloon out of control early, and then they come back down to earth and get small. All I care, remember, if I lop off the first part, it doesn't affect convergence or divergence, does it? So my terms at some point have to be getting smaller the rest of the way, even if they don't get smaller right away. So what this means is that after a certain point, it might be the first term, by the way. More often than not, it's probably the first term, but it might be the 10th term. It might be the 100th term. But at some point, my terms are all getting smaller in size forevermore. That's all I care about. That's what this is, for every n after a certain point. And again, more often than not, it's going to be the entire way. These two conditions are necessary if I'm going to have convergence, but they are not sufficient for convergence. So you never start a problem by trying to prove both of these are true. You never do that. You only do these if you think one of them is false, because then you're done with the problem. If either one of them is false, then you've just proved that it's going to diverge. Now, how come I say that's not good enough to have these? Let's look at, I don't know, how about this one? What is the limit as n goes to infinity of 1 over n?
That is 0.
0. So I'll put check. And is 1 over n plus 1 always smaller than 1 over n? Is the next one? Yep. So I just satisfied both conditions here. Therefore, oh, this still diverged, didn't it?
Yeah.
Satisfying the conditions doesn't mean it's going to converge. It means it's worth talking about. Us showing up for the game doesn't mean we're going to win, but now at least there's a game being played. It's the other way around. Us not showing up means we automatically lose. If I failed either of these conditions, then this automatically diverges, and I'm done with the problem. We like this test, but we only like it when it fails. Passing this test doesn't help me. You're going to learn 5 tests overall. Okay? And in some cases, more than one test might work. A lot of times, 2 different tests will work, so it's sort of whichever one you saw first kind of thing. If you're looking at the problem going, I'm not going to fail the nth term test, so I'm not even going to bother with it. I'm going to go right to the other tests that we're going to do. But if I'm looking at the problem going, you know what? I don't think my terms are approaching 0. Or I don't think my terms are getting smaller. Then I will go after that and be done with it, because that would be the fastest way to a conclusion. You with me on that? So we actually like that. So again, we call it's the nth term test because I'm taking the nth term, the general term, and I'm analyzing it.
I just had a fast backtracking question because I think I missed.
Say that 3 times fast.
The upside down A and then the little n big N. What does
Oh,
it mean?
upside.
in English?
This is called the universal qualifier. You want to get used to this one. This one means for all or for every. Does anyone?
Or
That one, the upside, the backwards capital E.
what?
That's
No.
called the existential qualifier. That means there exists. That's weak. There exists means it's true at least once. The other one says it is always. Those are kind of the extremes, aren't they? So that's called the universal qualifier. You should see this in your math classes in general, just because it's math people like shorthand. But you will use them more and more as your classes go on. So I like using them so you get used to it. This says, this is the n, right?
Yeah,
N,
N.
A1, A2, A3, A4, A5. At some point, there's a number. This big N would just be some constant. There is a point when they're always going to get it smaller. It might start right off the bat. Isn't this true for all n? For every n in my domain, which is all n greater than or equal to 1? So this was always true. What if it took a few terms before it was true? That can sometimes happen. Now here's the nice thing. You're going, oh my God, I'm going to have to solve an algebra problem to figure out, it's not true until the 11th term or the 23rd term. So let me just go out 100 terms. Okay, it's now true. I don't necessarily have to find the first occurrence of truth. I just have to show it's true from some point on. And that's actually a relatively low level thought that won't happen very often, but it will happen occasionally. Okay?
So to put it all together, that is saying absolute value of A n plus 1.
That means the next term is smaller
Yeah.
than or the same. The terms are another way of saying the terms are not getting bigger.
Yeah. And that doesn't have to be true from the first term, but at some
point it's got to be
it is.
true from that point
Okay.
on. I'll give you a really simple example of one of these. This is a really, well, okay, maybe simple is not the right word. This is one, we're going to look at things with factorials at some point. All right, so I have the following sum. I have 10 to the, I have 100, how's that? 100 to the nth power over n factorial. Okay? This is what we're actually going to do. We're going to do things like this all the time. Well, let's write the first few terms. So the first term would be 100 over 1 factorial. The next term is going to, or plus, let's say, 100 squared over 2 factorial. And then it's going to be 100 cubed over 3 factorial. I'm going to go out a ways. 100 to the 50th power over 50 factorial. These numbers are way beyond what any calculator would. These are beyond what a computer can now hold. Would you say these numbers are getting really big? Yeah. Yeah, they're getting really big. They're getting crazy big. And at some point I'm going to have 100 to the 100th power over 100 factorial. And then the next one's going to be 100 to the 101st power over 101 factorial, which is now
Now we're getting small.
smaller than this one. And forevermore, marked terms are going to be smaller. And believe it or not, they're actually going to approach 0. Wait a minute. These numbers are beyond reckoning. I mean, this is like to the sun and back, it's so big. You're right. But now they're getting smaller, and they're going to get smaller faster and faster and faster because I multiplied my numerator by 100, but I multiplied my denominator by 101. Then I'm going to do 100 and 102. Eventually, I'm going to do 100 and a bazillion on the bottom. You see where I'm going?
Yeah.
Now, my point
That
was,
makes sense.
I can't tell the behavior early because these look like they're getting big out of control. They are. But eventually they got smaller. So that's the whole point of this statement here. There was a point, namely after the 100th term, just so you know, that now they're getting smaller forevermore. So I actually passed both these conditions, and we're going to show later this actually converges. We don't know that today, but it's going to be an astronomical number, but it will converge.
Eventually.
Isn't that crazy?
Yeah.
It'll converge to a number beyond reckoning, but it will still be a finite value. Whoa. So it never matters what's happening early. It always, what's happening in that direction forever. So if it diverges, it's because the terms aren't getting small fast enough. Harmonic series. Every term got smaller, didn't it? But they didn't get small fast enough. We're going to prove this one next day, but I'm just going to tell you this now. This guy here converges. We're going to prove that next day. We can't prove it today. The sum of 1 over n diverge, but the sum over 1 over n squared will converge. But don't they have all the same numbers? Well, in a sense, but doesn't this one have a bunch of missing numbers now? So you went 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6. This one went 1 over 1, 1 over 4, 1 over 9, 1 over 16. I lopped off all the in-between numbers, didn't I? And lopping off all those in-between numbers actually will allow this to converge. We're going to show it. It's very simple next day. We're going to prove this. But the point being, some things can look really similar in nature but have completely different behaviors. One converge, one diverge. So it's never, oh, I think it's going to be this. We're going to be able to always show really, really clearly. Okay? I believe it or not, I think we actually know what this converges to. Not because we are able to do it. I think I saw a proof for this at a conference once. I believe this converges to pi squared over 10. I could be wrong. It's pi squared. No, it's not 10. It can't be 10. No, maybe it was 6. Yeah, by the way, you could probably look this up. I think it is 6, I think. Because pi squared is really, really close to 10. Because pi is really close to root 10. But you went 1 plus a 4th plus a 9th plus a 16th. Those numbers are getting really small really fast. I believe, again, I saw a proof of this years and years ago. I can't remember. It was kind of cool. Is it really important? No, because I can always use a computer to give me a reasonable estimation. One of the beautiful things is you're going to find, if we prove a series converges, not only do the terms have to be getting small, yes, I got that, they're approaching, but that means they have to be getting small really fast, much faster than the harmonic. And if they're getting small really fast, then it means changes in the decimal place are only occurring further and further out. So let's say for whatever you need an answer, but you only need a decimal answer. And let's say you need 10 decimal places. You need 10 decimal places. Yikes. Well, we'll actually have a way of determining when you've got enough terms to guarantee. And there's going to be problems we do where you might only need to go 3 or 4 terms. We're going to do things a little later. I might do 3 or 4 terms, and I'm going to prove to you that we have, 10, 12, 14 decimal place accuracy with just a few terms. When factorials are involved and things like that, the numbers are going to get so small so fast that the next number, is so small, and the next one after that's so much smaller that it's only affecting decimal places down the road. So even if you can't tell me exactly what the answer to a question is, you can give me a decimal approximation that is valid to any number of places that you want. You can absolutely guarantee accuracy to as many places as you want. And that is a very powerful thing. We're going to look at integrals a little later that have no antiderivatives. No, I call it the impossible question. We're going to be looking at impossible questions, questions that cannot be answered, and we're going to answer them anyway. We're going to take integrals that have no antiderivative, but do a definite integral and give a numerical approximation that is accurate to as many decimal places as you need. I can do 1,000 decimal places if you want. It just takes a little longer. But if you wanted 10 decimal places, we can get an answer in 2 or 3 minutes. And then we can actually verify them using the computer that it was accurate to that many places. It is so powerful what we can do with series. So all of the integrals that can't be integrated, a lot of them we can do this way. Okay, we can use series. We're going to learn that a little bit later. That's a few lectures away. Very powerful stuff. Okay, so we have 3 series that we absolutely now know the behavior of. Okay, we absolutely know the behavior of 3 different things. Telescoping, geometric, harmonic. We don't know any of the other ones yet. We're going to learn all of those in time. So, if I asked the following, determine the convergence or divergence of the following. Let's say n equals 3 to infinity of 2n squared minus 4 over 3n squared plus 2n plus 1. It would be totally okay for you to just rattle off the first several terms. But that really won't help me answer the question, because if you rattled off the first 1,000 terms, that does not affect convergence or divergence, that direction. So I'd like to know, does this converge or diverge? If it converges, I don't care what it converges to. That requires technology to give us an approximation. I'm okay with that. I can live with that. But I'd like to know if it diverges. Anybody want to tell me an attack strategy here?
You think limited
Okay, you said something about a limit. Limit of what specifically?
of that term.
So that's my nth term. So if I take the limit as n goes to infinity of this, what would I get?
Well, now we've got infinity over infinity.
2/3.
Yeah, isn't it just 2/3?
Oh,
Yes.
If you multiply